I'm Jeff Yarger. I'm a professor of chemistry, biochemistry, and physics at Arizona State University. This video is meant to introduce chemical kinetics with the goal of getting to looking at biological kinetics or biological catalysis, which is typically enzyme kinetics. But before we get there, it's important to reintroduce a subject that we typically see in introductory chemistry classes, which is the timescales for which chemical reactions happen and how they can be influenced. So in chemical kinetics, what we're always looking at is really the timescales at which things happen. And the variation is quite large from, timescales at which electron transitions happen, which can be, 10 to the minus 15 seconds or so, to things that are millions to billions of years, geological timescales or even astronomical timescales, et cetera, that we're looking at. So these timescales are quite varying, and it's important that we not only know thermodynamically if a reaction is favorable or spontaneous or not, but also the time at which it happens. This chemical kinetics and biological kinetics is a very practical and fundamental field to really give us a sense for not only if something's going to happen, but how much time it's going to take, et cetera. So again, we usually contrast this, and in thermodynamics, we're just looking energetically. Oftentimes, we're usually looking at energy and just asking energetically, is a reaction favorable? Does it lower the energy? Does it increase the entropy, et cetera? But it's typically, does it lower the overall energy? And often it's the free energy or the Gibbs free energy we're looking at. But just because something lowers the energy, for example, one of the classic things I always think of here is, because mainly it contradicts De Beers, diamonds are forever. Actually, no, they're not forever. In fact, they're not even thermodynamically the stable state, right? So if you just looked at thermodynamics and you looked at carbon in a crystalline lattice of diamond versus carbon in a crystalline lattice to form graphite, in other words, from sp3 to sp2 hybridization, and you calculated its free energy. So under constant temperature, under room temperature and pressure conditions, you would find, just from that equation, you would expect diamond to spontaneously convert, into graphite. So we would expect your diamond ring or your diamond jewelry to go back to pencil lead, However, we have an experience with this, right? We know that diamonds are very stable. And so it's not that they're thermodynamically stable, and it's not even just that the delta G is fairly small there. It's that kinetically, it's trying to do that transformation kinetically and having a large activation barrier between them. And so that's what we're really going to look at today, is to try to hone in on this. What is an activation barrier? Why can kinetics be so slow? And so that things that might not even be the thermodynamically stable state are, in a sense, practically, a stable material that lasts for a very long time, because it might only be a metastable state, but it's in a well that's deep enough that it's not the thermodynamics that dominates it. It's such long kinetics that allow it to stay stable for very long periods of time. And so what we mean by this, and I like to point out a more very common biological example here. Again, ATP, which ATP, ADP is what we think of as the energy molecule or currency, in a lot of living systems, especially us, right? But again, if you look thermodynamically at adenosine triphosphate, you would see that it hydrolyzes to diphosphate, and it has a huge negative delta G. There's a lot of energy to be gained by it spontaneously going in this direction. But ATP exists, with no problems at room temperature and pressure in your body. And so how do we explain that, And just like with diamond going to graphite, it's not that in this case, you would say there's a huge thermodynamic driving force to form ADP, diphosphate. But there's also a large activation barrier to doing this. And so it's that large activation barrier that makes this ATP, very stable under ambient conditions. It also, so that introduces this idea of activation barrier, or in a sense, a much larger effective delta G that you have to get over to be able to come down to the products. And so this brings up another important point, which is the way in which a lot of biological systems do this, which is to have catalysts, in a sense, what we think of chemically as catalysts. And we typically, in biology, these are enzymes. And so it's usually a catalyst that basically lowers this activation barrier so that it becomes thermodynamically driven. And it removes the kinetic barrier of this huge activation. So another way you can think of that is it would therefore require a very large temperature or extra energy to get over this, while what catalysts do are keeping temperature the same and lowering that barrier. That's what we're going to be looking at in this two-part video series. So when we look at chemical kinetics, what we're really saying is the rate of change of something. So the rate of change, and typically this is a reaction, so we'll just say, some reactants A going to products P, the simplest thing you can kind of write down. So we're looking at the rate of change of these concentrations. So we can say the obvious, which is the rate of change of A for this specific reaction will be, minus that of P. So in other words, these reactants, the products come as the addition, come at the cost of reactants being consumed, right? So they're equal and opposite. And we usually define the rate as minus this because we want the rate to be positive, okay? So, but it can change in several different ways. And so what we think of as the most obvious, which we often call zeroth order, is that, it's independent, that basically this linearly decreases the reactants and the products linearly increase. Now, it should be kind of obvious that you can only do this to a certain limit, right? You can only do this to the amount you started with of concentration. And at the limit of weak concentration, this can't keep going. It must kind of tail off. But this means a constant rate, right? Like that the rate stays the same. But you can have it where instead of the rate being, in a sense, independent of whatever concentration you're at the time, no matter if you're here, it's going at the same rate than if you're at half the concentration, etc., and the products are increasing linearly as well, the rate stays constant. You can have this where it's dependent on the first order. In other words, it's linearly dependent on concentration. You can have it where this comes as the square and it second order reactions, etc. Usually beyond zeroth, first, and second order is usually practically where most reactions fall. And we'll see practically actually, most reactions fall in first order. There are much fewer in second order and much fewer in zeroth order in general. And then there's a lot of nuances in between, pseudo first order reactions, etc., and also just how they happen. When you end up with multiple reactants and products, it doesn't mean that each of the reactant products are going at the same order. You can have one of the reactants going in kinetically first order while something else second order, etc. In other words, there are a fair amount of experimental complexities here. We're going to look at some of the generalities. So I found this out of Tinoco's book in physical chemistry for biological sciences as an example of first order. And really what I want to point out here is, so this is looking at the behavior of ethanol and as it, with an enzyme, as it goes to, as it reacts to form NAD+. So if we look at it with respect to the concentration, so again, the rate is defined by how some concentration changes with time. So it is linearly decreasing in the limit of very high ethanol concentration here. And this one is increasing at opposite that. And so it's at a constant rate here. No matter if you look at it initially or later on, it's still going at the same rate. But it can only do that. Obviously, you're going to run into zero amount of ethanol. And as it does that, it tails off. And if we blew this up, you would see that then the rate is changing disproportionately, right? So the rate depends on the concentration itself. And oftentimes, these zeroth order reactions at high concentration, high reactant concentration, turn into first order reactions where they depend on the concentration as you get in the limit of small amounts here. And often we're doing reactions in not the molar, the really high quantities. Often it is the millimolar, micromolar range in biological systems. It's one of the reasons that we can account for first order reactions being so common. And so this is an example of one where you can see data where it starts off at one rate, but it's changing. You can see now the slope, the instantaneous tangent here is changing. In other words, the rate is changing, and it's changing proportionally, with the amount of material there is, or first order in this. And you can see it in the numbers as the rate keeps changing, decreasing as you have less and less material. In this case, this is butyl chloride going to butyl alcohol. And it's undergoing, its rate of change is how the concentration changes with time, and that depends on first order, to a power of 1 or first order in the concentration of the butyl chloride. So when we look at this, again, when we talk about first order, where this x is 1, we looked at zeroth order, where the rate stays the same. First order, which is probably one of the most common for many type of both biological and chemical reactions. So it depends to the first order in the concentration of, in this case, the reactant. And so now what are we looking for to, in a sense, solve this differential equation? We're looking for something where when you take the derivative, you get the function back out. So we kind of already know what we're going to expect here. We're going to expect an exponential, right? Because it's one of the few mathematical functions where you take its first derivative or any derivative and you get the function back out. And this is just showing this formally mathematically, that if you look at this and we get, there's variables on the same side and we take the integrals, etc., that we can write this as the concentration, how it affects in time is the initial concentration, and it's the exponential of minus the rate times the time you're at. And so this is, in a sense, defining first order kinetics. We often write this in an ln form. We write it like this often because we're often fitting to a line where we're on the y-axis doing the natural log of the concentration, we're plotting it versus time, so that this would be the slope would be minus the rate constant. And then the y-intercept, b, gives the initial concentration. Or oftentimes we'll even plot this as a normalized initial concentration so that we plot it in a normalized way. So in other words, when we're looking at these reactants, it's changing. It starts off with an initial rate, but it's decreasing with time. The rate is changing in kind of an exponential fashion. And so this is increasing in an exponential way with 1 minus the concentration of A, right? So one's going up and one's going down. So one way, when we're often wanting to get this rate constant, it's related to if we plotted this as the ln of that concentration versus time, this would now be a line. We could fit that line with what I showed before to get out what the rate constant is. And that's the most common thing to do for first order, is we plot the ln of the concentration versus time. It's linear, and that's how we get the constant. We've seen, like, naturally the concentration versus time is linear in 0th order. And if we could do the exact same thing I showed mathematically for 2nd order, where you have now that concentration is squared, and you can solve that and see that you would be plotting the inverse of the concentration versus time. That would be a linear plot to give you what the rate constant is. And so this just kind of summarizes what I would call as the 3 0th, 1st, and 2nd order, the 3 most common rates you run across. One of the critical things, and this is rare, right? Like we think of, this is something where the units associated with it change, right? The rate depends now on what order it is, right? So 1st order is hertz or inverse seconds, but 0th order is the molarity per second, and then 2nd order is inverse molarity in inverse seconds. So you can also often tell by, you don't even have to state what the order of the rate law is. If they give you a rate constant, by the units alone, you can tell where you're at. What's very common, though, is to give you data, to give you, you experimentally measure some concentration as a function of time. And whether it's watching the reactants decrease in their concentration or watching the products increase, those are inversely related to each other. So in a sense, it really doesn't matter which one of those. We can look at those independently. And now we can look at either one or both of them. And this is what I call a very common thing to do. When you're just given the concentration versus time, you also make a column where you plot that concentration, and you plot that concentration as an inverse, and you plot it as the natural log of that concentration as well. So you make 2 new columns where you take the inverse of these versus you take the ln of these. And now you can just see by plotting the time versus each of these different on the y-axis, which one ends up linear. So you can see when you plot just the concentration, it's not linear at all, so it's not a 0th order. If you plot the inverse, 1 over the concentration, again, it's not linear either. It's not 2nd order. If you plot ln of the concentration versus time, you get a linear thing, and you can fit that to a line, and then it gives you minus 0.5. So the rate constant is 0.54 inverse seconds. And where it hits the x-axis would give you the ln of A0, or its initial concentration, where it hit time. It should be that. So this gives you a practical sense, because often what you're doing experimentally is measuring this. The other thing I like to show is if you're not able to plot something, this is just using something like Google Sheets or Excel to plot, but if you're not able to plot it, you can often just look at the instantaneous slope as well, or the tangent between just 2 points, and by how much they change. So this is just looking at, kind of y2 minus y1 over x2 minus x1. At one of the later data points, say 8 versus 10 seconds versus one of the earlier ones, 2 versus 4 seconds. And you can see, the slope changes a lot, meaning it's a much different slope here than here. It's a much different slope here than here. It should be a very similar slope here and here, but you can see like this data point is a little off, so you actually get a fair amount of variation. But the one that has the smallest variation in the slope is this one, and it indicates here. It also, I do this for a very specific reason, that these aren't exactly the same values, and they're not the value you get when you do all of them. If you basically took the slope of every pair of these and averaged them all together as an average slope, that's in a sense what you're doing when you're doing a linear regression. So you can see it really accounts for if one data point, this one happens to be a little lower than the line, it keeps you from getting fooled by a single data point that's a little off. It basically looks at all of them. So if you kind of did pairwise all of these different pairs, you would see that most of them fall right around 0.5 or so. But there is some variation, which shows you that if you only take a very small subset of the data, to use to get the slope and calculate the rate, that you can end up with a fair amount more error propagating through it than if you take all the data together. So the last thing is what we pointed out in the very beginning, which is the perplexing thing initially was thermodynamics. When we often talk about thermodynamics, we think we have the answer just by knowing whether something's spontaneous or whether something's thermodynamically driven or not. But then we gave some examples, both a biological one and kind of a classic geology or carbon, elemental carbon example, of ones that aren't in their thermodynamically most stable state at all. And we kind of explain that by saying that it's in a metastable state, and how metastable is defined by large activation barriers stabilize these metastable states and make them look thermodynamically stable, even though over there's a lower free energy state for it to go to. But it's very metastable. And so we can look at that experimentally by looking at the rate, which we just looked at, where we're looking at how the concentration changes with time, but now do it as a function. So do each of those experiments, but at different temperatures. And this is known as a Rainiest equation. Rainiest discovered this, that if you do this, you'll get how the rate changes with temperature. And you expect kind of the obvious. It increases with temperature. You get a faster rate the higher temperature you are. And it's because you can get over these activation barriers the more energy you are in this state. And by how much quicker you go over this activation barrier, you can determine what the height of that activation barrier is. And it goes exponentially, as you can see here. So we can plot ln of this rate versus 1 on temperature, and the slope will be related to minus the activation barrier over a constant r. So this can give us a direct by measuring different kinetic rates as a function of temperature. Plotting it in this way and fitting, we can get at what these activation barriers are, and hence, what type of temperatures you would need, etc. This leads us into the next subject, which is this is how you would get over these activation barriers thermally. But what we find is the whole area of catalysis is to be able to, in a sense, change these activation barriers. So to use another compound that lowers these activation barriers, lowers and raises them to make things where you can, in a sense, go to the thermodynamic state without having to go to high temperatures, just by decreasing the activation barriers. And that's what we're going to look at in the next video. But hopefully this gives you a general introduction to what is typically covered in introductory chemistry classes, and reminds us that kinetics is an incredibly important area for practically looking at chemical and biochemical reactions. Thank you.